When evaluating claims about an entire population's mean, denoted by the Greek letter mu, statisticians run into a practical problem. We almost never know the true population standard deviation, sigma. Without the exact population parameter, we are forced to substitute it with the standard deviation derived from our limited sample, represented by the variable s. Substituting a sample estimate in place of a population truth introduces a distinct margin of error into our calculations. To account for this added variance, we rely on a specific mathematical framework called the student t-distribution. As you can see, compared to the standard normal bell curve, the t-distribution is visibly wider and flatter at its peak. This wider shape intentionally reflects the greater variability we expect when using s as an estimate. Furthermore, the t-distribution is not a single static curve. It dynamically changes its exact shape, depending on the size of the sample you are analyzing. Like the standard normal curve, the t-distribution remains perfectly symmetric with a central mean of exactly t equals 0. However, its standard deviation continuously varies with the sample size and is always strictly greater than 1. But watch what happens as we increase the data pool. As the sample size n gets larger, the margin of uncertainty shrinks, and the student t-distribution mathematically converges, snapping perfectly into alignment with the standard normal distribution. Before utilizing this framework, two strict prerequisites must be met. The data must be collected via a simple random sample, and the underlying population must either be normally distributed or the sample size itself must be strictly greater than 30. The student t-distribution acts as a rigid mathematical safety net. It strictly prevents us from overstating our level of certainty when inferring absolute population truths from limited sample data. To execute a hypothesis test under these conditions, we calculate a test statistic using this specific formula. T equals the sample mean minus the population mean, divided by the sample standard deviation over the square root of the sample size. Let's apply this setup to a real-world case, testing a common recommendation regarding adult sleep habits. Our data consists of 12 randomly selected adults, yielding a mean sleep time of 6.833 hours. The specific claim we are testing is that the mean amount of sleep for all adults is less than 7 hours per night. We must first check our prerequisites. Our sample size is only 12, which falls well short of the required greater than 30 threshold. When n is less than 30, we visually inspect the sample data for normality. The frequency histogram on the left reveals no extreme outliers. Simultaneously, the normal quantile plot displays a linear trend. Together, these satisfy our normality requirement. Next, we formalize our parameters. The null hypothesis, H0, represents the condition of equality, mu equals 7 hours. The alternative hypothesis, H1, reflects our specific claim, mu is less than 7 hours. Because our alternative points specifically below the mean, this dictates a left-tailed test. Defining the hypotheses and verifying data structures first guarantees the mathematical integrity of the entire test before a single computation is run. We pass our specific variables into the t-test equation. Taking our sample mean of 6.833, subtracting the hypothesized mean of 7, and dividing by our standard error yields a resulting test statistic of t equals negative 0.290. We now evaluate this statistic against a predefined significance level, which we will set at alpha equals 0.05.
We can determine statistical significance using 3 mathematically equivalent methods. This image displays outputs from common statistical software using the p-value method. The technology calculates a p-value of 0.3887. Because this probability is greater than our 0.05 significance level, we fail to reject the null hypothesis. The critical value method maps a physical boundary region onto the distribution curve. The green area represents the rejection region, bounded by negative 1.796. Our test statistic of negative 0.290 falls short of this boundary, leading to the same conclusion, failed to reject. The third approach is the confidence interval method. We construct a 90% confidence interval spanning from 5.80 to 7.87 hours. The null hypothesis of exactly 7 hours fits inside these limits, remaining a plausible value for the true mean. Regardless of whether you analyze p-values, map critical regions, or plot confidence intervals, the mathematical truth is perfectly consistent. There is simply not enough statistical evidence to prove that adults sleep less than 7 hours a night. Let's run a rapid contrasting case study. We will test the common societal belief that the mean human body temperature is exactly 98.6 degrees Fahrenheit. We collect a larger sample of 106 subjects. This yields a sample mean of 98.20 degrees, with a standard deviation of 0.62. Because this sample size easily exceeds the strict threshold of 30, the underlying normality requirement is automatically satisfied. We bypass the visual plotting step entirely. Our null hypothesis states that mu equals 98.6. Because our alternative claim does not specify a direction, we split our alpha level, dictating a two-tailed test. Passing our variables into the formula yields a highly extreme test statistic of -6.64. This result triggers every metric simultaneously. The p-value calculates to absolute zero, the test statistic breaches critical boundaries, and the confidence interval excludes 98.6. Because all three evaluation metrics violently trigger a rejection of the null hypothesis, the data points to a single definitive conclusion. We possess sufficient mathematical evidence to state that the 98.6-degree standard is false. The rigorous procedures we just executed apply to the overwhelming majority of real-world scenarios, those where the true population standard deviation is an unknown variable. However, we must address a rare statistical anomaly: how to evaluate a claim when the population standard deviation, sigma, is already perfectly known. In this specific scenario, the foundational prerequisites remain completely identical. You still require a simple random sample, and the population must either be normally distributed or have a sample size strictly greater than 30. What changes is the mathematical distribution. Because we have the exact population parameter and no longer have to estimate the standard deviation from a sample, we do not need the wider variability buffer provided by the student t-distribution. Looking side by side, the sample estimate S is swapped for the known population parameter, sigma. With this parameter, the formula calculates a standard z-score. We revert to the standard normal distribution, evaluated using p-values, critical regions, or confidence intervals. Whether substituting sample estimates with t-distributions or utilizing known parameters with z-scores, the logic remains consistent. Hypothesis testing provides an uncompromising algorithmic mechanism for separating flawed assumptions from statistically validated truth.